from Florida. It's my great pleasure today to introduce Professor Andrei Shelnikov from Georgia State University. And he's going to talk with us today about GPU-based tools for studying multiscale and complex dynamics. Okay, thanks.
You're welcome. Actually, I will try to, okay, I'm muting myself now, right? Okay, I will try to give two talks actually today. So the talks from the past. So one is that that's what my real life, and the second talk is my hobby already. Okay, hopefully, right? And I'm going to put emphasis upon how we use parallel simulations, especially GPUs, in our research, right? But it's all started like what 10 years ago, even more than 10 years ago. All right, so this gentleman, okay, used to Schwabedal. It's actually he was a driving force. So he came and he was a postdoc in the lab. And at that time, I didn't know anything about GPUs. And used to use just NVIDIA video cards as GPUs to run simulations, right, on the video cards, right? And then after that, I started collecting proper GPUs like Teslas and Kepler and all that stuff. So, okay, so just a few comments. So hopefully I have 30 minutes to finish part one, and then 30 minutes to complete second part. So what you see here, right, this animal is called CSLAG, and it has a neural circuit that we call central pattern generator. And that neural circuit generates the pattern. You see it on a black square. You see this kind of, it's called bursting activity. So whenever this animal swims, the central pattern generator generates the outcome. So the CSLAG Tritonia, it has roughly 60 seconds to escape from the C star, which is a predator. Okay, and after that, that outcome is gone. So the only reason why I'm showing this picture is to show that the circuit that controls the swimming pattern, it looks like a triangular shape. It has DSI cells, right? It's basically just 3-cell network. So that's the main reason. So another example of a celebrity CPG network in the world, okay, it's called the pyloric central pattern generator. So the animal that you see here in the picture, right, also known as a lobster or mar, it has teeth in the stomach. Picture on the left. Okay, so let me see it. Okay, this one. Okay, I got it. And
the slides are not changing.
That's how it crashes the food. So there's a middle tooth and it goes up, and the two bilateral teeth, they go down, and that's how they crash the food. And then the
not seeing the screen change on Zoom.
You don't?
Are you sharing your screen through the Zoom call?
Yeah. Okay, so you don't see that?
No.
Okay, that's interesting already. Let's do it again. I'm sorry.
Oh, no.
Now you see it?
Yes.
So you don't see it when I do the full screen, correct?
No.
All right. If I change it now, do you see it?
Now it's good.
Okay. So I'm not going to use full screen then. Okay. I'm not going to use full screen. Okay. So that's okay. That's what I was trying to say. The circuit is.
Maybe if you maximize it, you windows.
I did that. Okay. Now.
Right on the very top of this way.
But now you don't see the change.
No.
Okay, which means you don't use a full screen. But I'm going to maximize it.
Yeah. All the way the top right corner.
Top right corner. Top right corner. I think that should be fine, right? Okay, so I go back to the slides. So that's what I meant. This CSLAG is called Tritonia. It has a neural circuit built in it. It's called the CPG central pattern generator, and that CPG controls the swim behavior. And whenever this animal swim, that neural circuit generates this rhythmic activity that you see here, right? Like on recorded simultaneously from 3 cells. And there are phase relationship between these bursting cells And basically this constitutes the swimming pattern of activity. And this episode of swimming lasts around 60 seconds. That's how much time Tritonia has to swim away from the predator, which is a sea star. So another example of a CPG, okay, so lobster, it has teeth in the stomach. So the CPG that controls the locomotion of the teeth is called gastric meal. I mean, it makes sense, gastric meal. And then there's another circuit, like this triangle, and that triangle circuit is called a pyloric CPG, and it generates this three-phase rhythmic outcome, and that CPG controls a muscle that contracts, and basically the muscle is like a sphinx that's supposed to suck in the garbage from the stomach and throw it away. So it's like 1, 2, 3, boom. So what I'm trying to say is that the three-cell network, they're typical for neuroscience, right? So don't get surprised. Okay, so, and these cells, these circuits are monostable, meaning that they're supposed to generate one rhythmic outcome only, but they have to do this stably. Okay, so let me go and show the first example. That's how we basically introduced parallel simulations in our research. So we consider this three-cell network. Each cell, blue, green, and red, it's endogenous burster. So basically they generate this voltage races, right? You can see this spikes of activity followed by the quiescent period. So nowadays we don't show the equations. We show the equations, but we show movies. So these three cells, the way they communicate, whenever cell is active above the synaptic threshold, it's going to send a synaptic current to the other two cells. So these two inhibit the red cell and it stays down. Okay, now they're all below synaptic threshold. They don't talk to each other. Okay, so you can see episodes of red followed by all together green and blue, now red again. And what you will see that when they coupled, they communicate, and this communication results in a this rhythmic outcome that we call indirectly, right? That's fine. Okay, we call this half center, or not half center. We call it pacemaker. One cell burst against the other two in synchrony. Okay, and then what's going to happen in that movie and reflected in a trace in the top right corner, then I'm going to apply a negative pulse to the blue cell. You see, I shut it down, it went down. Okay, and then I slightly speed up the movie, and then I'm going to release the blue cell from inhibition. Okay, I'm not using any neuroscience terms here. I release it, and then I still have three-cell network. Okay, and what you will see here is going to be something interesting. Okay, so let's say now blue fires, okay, and green and red are waiting here. So in our terms, in dynamical system terms, when blue fires, right, or whatever cell is up, it narrows the gap. It creates a bottleneck effect. So that's cell node bifurcation, basically. So this gap. Now green cell fires, bursts, and these two are waiting at the knee point, ready to jump. Okay, who's going to be next? And what you will see that the next is going to be a blue cell again. So the red cell that used to be active burster and a pacemaker in the network now will be shut down completely for the rest of the simulations. So as you can imagine, that this neural network is not monostable. It can produce rhythmic outcome when you have a red cell firing followed by the other two. Okay, and then when you change slight initial conditions, then blue and green cells, they will be burst in alternation, and they're going to shut down the red cell forever. So what is shown here on below, it's a voltage traces from experimental studies. Okay, this is done by in a lab by Ron Calabrese and Emery. It basically described the blood circulation in a leech. So, and it's, as you can see, it's very similar pattern. I don't want to go into details, but just to tell you that the similarity is obvious, but I can't tell you that what you've seen now is really the solution of the blood circulation CPG that Ron studies in his lab. Of course, it's just It's just a coincidence, right? But it's an interesting coincidence. Okay, so you've got this part, okay, and the next step is that, all right, I have Hodgkin-Huxley bursting cells, and I'm going to talk in a second what you see on the right. And then if you use what's called bottom-up approach, you start with the grounded models, biologically plausible, and then you will try to find what matters for the retrogenesis in such three-cell network. Okay, so this is a connectivity. You can change the coupling strength between the cells. So far, everything is symmetric. And then you use what's called generalized Fitzhugh-Nagumo. Fitzhugh-Nagumo, also known as the relaxation oscillator. You know, this is a cubic null line. Okay, and in addition, there's another line shown as orange, right? In two-dimensional system, it's a kind of old story. And basically what happens is that when, say, green cell is on the top, on the upper branch, it sends a perturbation onto the blue cell, and that perturbation results in narrowing this gap, which means it creates a bottleneck effect, which means blue cell will be delayed, okay, or we say inhibited by the active cell. And then what you can do also, right, you can create even a simpler model, which you call 2 theta neuron. Basically, you're running on a unit circle, okay, and then there are two, I mean, it's like Atlanta's Highway 285, and then you have two stagnation areas next to the airport at the bottom, right? And then this is where the 400 crosses, right? And always there's a traffic here, right? So which basically means whenever the cell slows down, okay, you have this upper plateau, and then inhibit the other two cells, creating a bottleneck effect, and they're waiting here, okay, to generate, and then they're gonna get released as soon as green cell goes below synaptic threshold, and then they're gonna run and inhibit the green cell, and that's how the game continues. And basically what I'm gonna show next, okay, that's how we approach this, and that's how we introduce CPGs. So basically, I already said that very likely that the circuit can be multi-stable, it can produce more than one rhythmic outcome. And we wanted to develop the tools that are neuroscience appropriate. And the way we do it, we introduce, okay, the time delay. So for example, you pick a blue cell as a reference cell, and then you measure the delay between, say, burst or spike origination in the green cell in the red one, so that tau. And then you divide the tau by the recurrent time, by the period of the blue cell, and you have what's going to have a phase lags, get defined on modulo 1. And what you see here, if you run some initial conditions, right, and you just follow the phases between the cells relationship, so you don't care about Hodgkin-Huxley or anything else, you will see that sometimes the phase, okay, the phase difference, you see it converges to some kind of flat line. You just call phase lock state, okay? And then there's another line, which is a phase lock state. So this is phase difference between cell number 1 and cell number 3. And this is the phase differences between cell number 2 and cell number 1. But then you exclude time, and then you have this square, a unit square, which is a two-dimensional return map for the phase lags. And you have a fixed point. This one is stable. Okay, that one is also stable. We're going to say what it means. Okay, and then you have another stable, and you have multiple. You have several stable fixed point. But if you have stable fixed point, you must have unstable or several fixed points. So, and the incoming separators on incoming stable sets of these saddles, they determine what the boundary of the base instruction is going to be. So you have to be in a, I mean, so basically picture on the right means that you're on a torus, but nobody wants to look at the torus, right? You will flatten this, and this is your unit square. But my point is that every fixed point in a classical synchronization theory, which is a phase locking state, it basically means that if I introduce some kind of abstract parameters, I'm sitting inside what's called synchronization zone. Okay, but some people call this Arnold tongue. So if you happens to be inside the tongue, that you have a stable fixed point, and when you change the parameter, say connectivity strength between two cells, you cross this the borderline, the boundary of the Arnold tongue, and then what's going to happen? You're going to lose that fixed point. And how? Because this saddle is going to merge with this this stable fixed point. The merge disappear through the cell node bifurcation. So all I'm saying is that it's been around. The whole synchronization theory, right, is well known, and we just use it in applications to neuroscience. Okay, so and I'm going to show you the movie. So and now you can see why we use GPUs. At that time, Jeremy Logic, who was my PhD student at that time, he did this movie, okay, and that movie basically let the ice between us and neurophysiologists melt. Okay, so as you can see, this is a voltage race. You measure these delays, okay, and in the return map, you see trajectory that converges to this fixed point. If you look at the coordinates, you see 0 and 1/2. 1/2 means that the phase difference between the reference cell blue and red is 1/2, which means they're bursting in anti-phase, and these two are fighting together, which means they're in phase. That's how you interpret the coordinates. Now you pick another initial condition, right? And then you see the green trajectory that bends to this point, okay? And then you have another fixed point, okay? And then you run another initial condition, and it converges to the blue point in the middle, and its coordinates 1/2 and 1/2, which means blue cell burst in anti-phase with the other two cells of the network. And in addition, you pick initial point in between, and that's going to converge to another fixed point here. And if you look carefully, you will see that it's a blue followed by green, followed by red cell, followed by green cell, and you will see the coordinate of this fixed point. It's a 2/3 of 1, which means it's 2/3 of the period, right? And this is 1/3. And this is called traveling wave, or in neuroscience context, we call this peristatic rhythm. And the network is more or less symmetric, right? All connections are more or less the same. And then clearly, if you have a traveling wave moving, say, counterclockwise, then you must have a traveling wave moving clockwise. So now you can see why we use GPUs, because in the GPU, you can run the initial conditions in parallel. And if initially it took Jeremy, I don't even remember, say 1 day to generate a pattern like that, if you're accurate, I mean, maybe not 1 day, maybe a couple of hours. On a GPU, you can do it in a split of a second. And Krishna, hopefully, next week, he's going to tell about how he did it. Okay, and basically what this allows you to do, okay, you don't have the right-hand side to generate this map. Actually, we can feed the right-hand side, but it's not worth it. Because if you feed the right-hand side and you change, say, coupling strength or some intrinsic parameter to the cells, this map pattern is going to change, and then you have to redo your fitting, right? And it's not worth it. What's worth it is just to run it in GPU, because it takes a split of a second, right? And you know what's going to happen. Moreover, you understand how it works. I'll give you an example, okay? So you pick up a symmetric circuit, and then you increase connectivity between cell 3 and 1. So basically what you see, I'm going to break a symmetry in a clockwise direction. As a result, this fixed point that corresponds to the traveling pattern in a peristatic rhythm moving in a clockwise direction, you see that if I increase the coupling strength slightly more, then these two fixed points, stable and the saddle, they're going to merge and disappear, and then its base of attraction now belongs to the red point. So red point is kind of the strongest fixed point in a map. But then you keep increasing this, okay? And what happens is that, remember, there's a red point means that red cell burst in anti-phase against blue and green cells bursting in phase. But it can't keep them, it can't burst, you can't inhibit them equally, which means that rhythm is going to also disappear, right? And if you increase the coupling strength and you cross another borderline of the synchronization zone, then the red point is going to merge now with another saddle. That's why you have a saddles, and disappear. And now you have this pattern. So basically, you have now intuition or knowledge or skills to tell how the network can operate. Okay, and then users brought it to the level of a computer game. So you can download his code and run it on your laptop. And the question that we ask every undergraduate student who join the lab, they play this computer game and say, okay, can you make a network? Can you create a network that has one stable fixed point, so it's monostable? Or can you get a network that doesn't have any fixed points whatsoever? It has a pattern of activity like this, right? It's called, you see, it looks like it's a periodic activity on a torus. You start here, you move down, okay, and then you're going to re-emerge back at this position. And the way the network transitions to this invariant curve is that you have two saddle nodes at the same time. There is a heteroclinic connection between these 2 points, And as cell nodes disappear, that heteroclinic connection results in the emergence of this stable invariant circle. So bottom line is that, I mean, if you look at our publication, you will see that we studied that in a full details. Okay, just one example, just showing a network that doesn't have a fixed point. You transition through the ghost of this fixed point, then transition to the ghost of that point, you see the pattern, and then again transition to the ghost of another traveling wave. So you'll see the blue, green, and red, and then you're going to go to the green pacemaker, and voila, and then you repeat the pattern. So that's what I said. That this is Eustace, and this is my lab, and then he teaches us how to use his software, which is a computer game. So what you can do, you can change the properties of the cells, you can change the connectivity, and you'll get a pattern like that, right? And then you create what's called, we call it political map of Europe. You change this connectivity, and you're losing the blue region, for example. Why? Because it merges with the saddles, right, and then disappears, right? And on a Tesla, and then Tesla has what's called academic donation program. So these cars used to cost $7,000, but they're worth it, right? And we use them all the times to basically quickly create quickly understand what's going on with the circuits. And even though it has nothing to do with the research that we are doing now in the lab, nevertheless, it taught us a lot. We learned a lot through modeling studies of this network. And what I said earlier, whatever I said, it's true for three-cell network, either made of these toy models we call two theta bursters, or Fitzhugh-Nagumo, or Hodgkin-Huxley, or you can even pick other Hodgkin-Huxley models, right? All you have to do, you have to make sure that there is a gap here, and that gap narrows, which means it's going to slow down cells at this knee point, and that's how we create these patterns of activity. And Krishna is going to talk next week about his research on four-cell network, which is kind of extension. And once you have this, okay, then you can create a bifurcation theory of a neural network in terms of return maps. So we no longer look at the traces, we just look at these maps, and you can see that depending on the intrinsic parameters of the cells or coupling strength, you're going to get the patterns. For example, if you look at the panel A4, you can see that there are only two traveling waves, clockwise and counterclockwise here, and you don't see any pacemakers. On the contrary, when you look at map G1, you will see that you do have traveling waves, they do exist, but they are unstable, which means these fixed points are actually unstable foci. Okay, and then you can study all these transitions in a symmetric network, right? Or you can create asymmetric networks, okay, and create a bifurcation diagrams for the neural network, right? And then if you're interested in some fancy stuff like heteroclinic, homoclinic bifurcations, you will see that they're super duper important for neural networks, which is kind of amazing, right? But then you have to stop here, because if you want to deliver that message to your friends neurophysiologist, right, it's way too much. Okay. On the other hand, for mathematicians, it could be also way too much because they don't know neuroscience. So just another example, just to emphasize the role of heteroclinic bifurcations. So look at this map. You can see that it's mostly populated by the blue color, which means the base attraction of this point is largest. And then little bifurcation, all of a sudden, the blue base attraction shrinks and the green base attraction extends. Why? Because there is a heteroclinic connection between these saddles, right? So saddles always behind transformations of global transformation, not local. When I say local, I mean saddle node bifurcations and basically other things like invariant circle that corresponds to torus bifurcation. And we had a challenge in the lab to create a configuration of the network when you don't have any fixed point whatsoever. So which means you get rid of each fixed point one by one by changing, manipulating the connections. Right now, I'm just saying that it's random. No, it's not random. You have to think how you do this. So you eliminate them through the cell nodes, and then you have invariant circles. As you can see, this one is stable, then you have unstable, and life on the torus is very special. So, which means that if you have fixed points on the torus, that the number of what structurally stable fixed point must be even. Okay, and the number of invariant circles must be even. That's why you have them in pairs. And all you have to do now, you have to create a network when these two invariant circles, stable, unstable, merge and disappear. And now we have what's called a notion of automorphism of the torus. So it's just fun part. It has nothing to do with neuroscience. Or, okay, or you can create even more interesting configurations when you have what's called cherry flow on the torus. Maybe it's the next slide. Okay, this is the cherry flow on the torus when you have a stable fixed point, but you can't get it in because it's kind of bounded by the separatrices of the saddle, right? And that's how it transitions. And the fact that you have in a torus, you can always stick together these panels just to see how the torus, how these trajectories, special trajectory separatrices, they fill in, populate the torus, and how they separate the Weissman attractions of the fixed point, and so forth and so on. So again, GPU was a great tool for these kind of studies in parallel. And what I was trying to say, let me see how many slides I have more, is that, okay, the interesting part of the story was that if, for example, you make connections, if you change the nature of connectivity, instead of inhibitory, you create excitatory, this would be equivalent of reversing the time on the torus. So for example, this point that used to be stable now becomes a repeller, okay, and the point that used to be a repeller, unstable, becomes stable, but saddles are always saddles in the backward and the forward time. And again, with GPUs, you can easily do that. Okay, then I'm gonna skip this slide. Krishna is going to talk about this. He's going to talk about this. And this was photograph taken back, like, I'm thinking maybe 10 years ago, maybe 7 years ago. And that was the day when Drake and Ian had a birthday, and then Denise baked a cake, and you see the pattern. And the idea was that for us, 3-cell network is just a piece of cake, right? So we knew everything about that stuff. Okay, so that's a kind of completes the first part of the story, how you can use GPUs to run simulations, right? Especially of the network that are multi-stable. So that's why you have to use multiple initial conditions, right? And then you can sweep the parameter space of this network. Let me go back to the slide to show that in this area, I have mostly pacemakers. In this area, I have mostly traveling waves. And as I said, you can study bifurcations indirectly. There is no way you can do this using any parameter continuation tools like Auto or MatCont. So you have to develop it, because again, these are the networks, okay? And these are coupled system. And if you have, again, if you have a simple model that Hodgkin-Huxley has type, and it can be complicated model, but again, you don't really care. All you care is that, again, phase difference between the burst initiation in a cell, and you will see that bottom-up approach works just fine. Whatever is true for biologically plausible cells is also true for the toy models as well, which means you nailed it down and you know why and how it bifurcates, which means you have what we, again, neuroscience call power of prediction. You can tell what's going to be next. Okay. All right. So this is my first part of the story. Do you have any questions about the first part by any chance? All right. I can't hear any questions. So what I'm going to do, okay, so I need to go to Zoom, and then I want to say, not stop video. I have to new share. No, not new share. Okay, I need to stop sharing, stop share here. And then I'm going to minimize this window, and I say, share the screen, and I'm going to share that screen and share. And okay, maximize it. Hopefully you can see this, right? And this is the second part of the story. Again, this is my hobby already. So it's all about how we approach, how we model, how we try to understand deterministic chaos. When I say deterministic chaos, I mean that no noise, nothing, right? You have let's say, canonical models like Lorentz equation or Rosler or other similar system, right? And you want to know why it's chaotic, what are the organizing centers of chaos that create instability in the system? Can we understand that locally? Can we put the picture all together? These are just examples of what we're going to talk about. Okay, and these are two represent examples. So picture on the left is I think it's a Lorentz equation. Picture on the right is Rosler. And the way we introduce symbolic representation for trajectories for Lorentz is kind of obvious, right? In this particular case, I mean, it's not that simple always, but from now on, let's just say that you have this butterfly. Oops, move up. You have this butterfly, and whenever you make a turn around the right on the right wing, you're going to place 1. Otherwise, it's going to be 0, and then you have a sequence of 0 and 1s. Okay. Which is kind of obvious again, and symbolic dynamics was popular back in the 80s, right? In the 70s, or not in the in the 80s, 90s, and now there are tons of questions. What is what's called sufficient partition? Is it partition that is sufficient to understand everything, right? Should you make it more accurate or might refine it? But we're going to come back to this later on. And for the Rosler, we use the Z variable and basically in a very engineering approach, right? Should be good for Georgia Tech, right? Engineering school. So if oscillation is below some threshold, you're going to put 0. I mean, of course, right? The 0 means that you spiral away from the saddle focus, which is going to be a Shilnikov saddle focus after my death. Okay, and then you go on the big excursion, and then you place a 1, and then you come back and place 0. That's how you generate a sequence of 0 1s. Okay, and the idea, okay, I'll introduce it quickly, right? Once you have this binary sequence, you have options. Okay, sequence is simple, okay, piece of cake, right? What you do is just save it as an ASCII file on your hard drive, and then right-click on the file and say zip it, right? And then you have zip file. And if zip file is way smaller than the original sequence, which means zip archive did a good job, right? Which means sequence is simple. And you just use what's called a single pass. You have a one option to save it. But if the sequence is like a white noise, and you don't see long sequence of ones like here, okay, like here, then it always changes signs. Then it's going to be a very difficult sequence to compress. Okay, and that's how we introduce. I mean, you can use entropy for this purpose, right? You can use multiple algorithms like Lempel-Ziv that was used in the GIF file. You can use all of them to figure out what's going on with the sequence, right? Whether it's simple or not. Hopefully, Krishna also will address this. So we found that Lempel-Ziv or block entropy is just a perfect tool for that. Okay, so when I'm going to introduce this simple model. Is called Shimizu-Murioka. I mean, basically it's a Lorentz equation. It's very similar. It's kind of a normal form in terms of mathematics, right? As you can see, there's a Jordan block, the linear part written in a Jordan block, and then you have, of course, the equation that is asymmetric. And this model, like Lorentz attractor, generate this pattern of activity. And what people do, they use what's called Lyapunov sweeps. They measure the average rate of divergence of convergence between trajectories. So if, say, this initial distance always is going to be larger than this distance after some integration time, right? They're very likely going to converge to a stable equilibrium state, right? So basically, that's how you introduce this Lyapunov exponent. It's a ratio of these distances, right? And then you take a log. If this ratio is less than 1, the log is going to be log of this is going to be negative, and then you scale it by time, because again, it's so Lyapunov exponent it's a 1 over sec or whatever. If on average the distance doesn't change, which means you're staying on a periodic orbit, and if distance on average increases, then you are in this red area, which basically means that you have some kind of chaotic dynamics in that area. And then you see, all right, I have a solid region here, right? And then I have some stability windows like flames. Where do they come from? Why? What happens when I cross this borderline? What happens when I this borderline? Why? I have stability windows in the middle of my chaos, right? I didn't see them before. And these are the questions that we would like to address. And again, this is typical approach I never liked Lyapunov exponent. I'm sorry, right? I'm going to tell you that we found a easy way or alternative way of using Lyapunov exponent, and then I go back to this slide, and the idea is that okay, you run this trajectory for a while, then you truncate it, you just remove the transit part, and then focus on the remainder, and again, then you have two options. Okay, the sequence looks like it's chaotic. Okay, one option, or it converges to some periodic pattern like 1 0 1 0 or 1 1 0 1 1 0, right? Which means I'm in a periodic orbit, and periodic orbit in a parameter space, right, is structurally stable, right? Which means Lyapunov stable, which means it's going to fill some regions in the parameter space, and that's how you can change the parameter, and you have the same sequence, which means I'm sitting inside that stability window. So you can use symbolic approach to detect the stability windows. We're going to talk about in a second. So if you, again, but still there's room for improvement in terms of Lyapunov exponent, right? If you refine your kind of accuracy of Lyapunov exponent, you will see that, okay, I have chaos in this region, right? Which is light blue, which means it's a cold chaos. And then chaos becomes really hot in this area. Why is that? Right? And then we're going to answer the question. I mean, we're going to answer why it's a hot chaos in this area, and then you will see that in a second. Okay, so then I go back to the slide to introduce symbolic description using ones and zeros, and you see the same picture of Tesla, and Tesla was instrumental. Tesla GPUs was extremely instrumental to better understand what's going on. And I waited for nearly 20 years, right, to revisit my old research when I was a PhD student, okay, and then I started this Shimizu-Morioka model, and it's all about homoclinic bifurcations of certain codimension 1 and codimension 2, and you see this is my this is a bifurcation diagram that I did, pulling each line one by one, and they all have meaning. I mean, they have the spirals, they all have meaning. All these lines have meaning, right? They tell you what's going to happen, right? But on a GPU, as you can see, you can get this picture. You don't have follow each line one by one. You create a mesh of points in the parameter space and run simulations. And for example, in this blue area, you converge to the equilibrium state everywhere. In this area, you can converge to a stable periodic orbit. That periodic orbit undergoes a sequence of period doubling bifurcation, and our symbolic approach doesn't detect that, but we didn't want to detect it even, right? So we just say, I have a periodic orbit here, right? In this area, I have chaos, and now you can see that this is the mystic chaos. This area has a structure, and the structure is not random, right? It's kind of self-similar structure. What's going on at this point? Why is that? Why all these lines converge to these points, right? What is saddle here doing, right? It kind of redirects the bifurcation lines in a parameter space. Oh, that's interesting. Okay, and now you can raise interesting question, right? So, for example, before GPUs, Tinglier, who did the sweep, Tinglier, she came to the lab. She was assistant professor back in China, and she knew the theory of pk iterates, the classical differential equation theory, right? But she didn't know how to solve a simple linear differential equation, just constant coefficient. And of course, she had no clue how to program. When she created her first piece of code, she saved data, each 0 or 1, she saved it as a separate single file on a hard drive. Guess what, right? The hard drive was ruined because nobody, a bias, couldn't read it, right? It couldn't read the catalog. So I have to throw it away. But soon she got the skills, and it took her almost a month to get this diagram. So this diagram is made of 40 panels. Each panel includes like 4,000 or points or 4,000 by 4,000. So you can zoom it in and you will see all the details, right? But that was the game. At that time, we didn't know how, for example, to introduce the scalars. What do you mean by that? Okay, let me go back to the slide. So you have a sequence of 0 1s. You can treat it as a real number. You convert binary into decimal, right? But then it's going to be huge, right? Because, okay, and then you have this range of numbers from 0 up to whatever billions, right? And how are you going to pick the color? So the idea is that it was proposed back I think it was Turnstone and Milner, who introduced what's called needing invariants. So basically, you create a formal power series. So Q is a number that is less than 1, okay? And then you create a convergent power series, right? And that power series converges, I mean, you truncate it, right? You're going to get some number, and that number, you map it into the color. So for example, say all zeros, you're going to get blue. If it's all ones, you're going to get red. And then you have all colors in between. And that's what you see in this bifurcation diagram. So colors, the colors in this picture have no meaning whatsoever. Your goal is to make sure that the color map is not continuous. So you can see the difference. You have a difference. You can see the difference between the lines, and each line corresponds to a homoclinic bifurcation. What is that? So, for example, this primary line means that it's a primary homoclinic bifurcation. Then you have a secondary homoclinic bifurcation when trajectory comes back like this to the saddle, and this corresponds to a sequence 1, 0. And then if your sequence is going to look like 1, 0, 0, 1, and then even longer, say 1, 0, 0, 0, that sequence with infinite number of zeros is going to correspond to these points that looks like a stable focus again in the parameter plane, but it's not. Okay, but at that time, I'm not telling you how we interpret this. And you play this game like Olympic Games. Can I do better? Can I get more colors? Can I get a better resolution? Can I, right? And then when you make the sweep longer, so you want to detect more accurately and longer homoclinic bifurcations, okay, so kind of length 14, all of a sudden you're going to get this noisy area in this area. And okay, why is that? Because there are so many color changes in this area. That's why it creates an illusion that it's noise. And if I only zoom this part in, I will see that, right? Okay, so, and and what I'm skipping this part, but this spiral that corresponds to what's called T points, heteroclinic connection between the saddle and the saddle foci in a Lorentz-like system, and I know the theory at this point, right? I know the theory of this point, but how they connect it, right? Nobody knows. It's called global bifurcation unfolding, and we use GPUs to understand this better, right? And the interesting part of the story is that, for example, all these lines, they stay with a certain area, certain weight in a parameter space. Again, it comes from the theoretical studies done in the 80s by Bykov he was a student of my dad back then, right? Like in 85, 87. Okay, so all right, let me skip this part. Okay, so one way you can analyze the complexity of the binary sequence is you introduce what's known as a Lempel-Ziv complexity. It's basically, it's a Shannon entropy up to a certain extent. And it's going to tell you, for example, this sequence, is it periodic or not? What's the complexity of the sequence? So when I explain to undergrads what a Lempel-Ziv basically means, that you have a textbook or novel, and then you don't have a glossary in the novel, right? You have glossary only in the textbooks. Okay, you don't have glossary in the novel, right? And the book can be 500 pages, right? But it can be only "I love you," right? Which is a love story, right, and nothing else. Which means the context of the book is simple, right? It doesn't use any extraordinary vocabulary. So that's how you introduce basically vocabulary. So what words or sentences it's made of. And this sentence is made of 8 words. You can divide by the length of the sequence, and it's going to get you basically the Shannon entropy or block entropy. Okay, so I'm skipping this part, just block entropy, how we define it. And my point was that you can use block entropy, you can use Lempel-Ziv complexity. This is just a one parameter sweep of the Lorentz model, just one, you change the parameters. You can see that in this area, I have chaos, chaos, chaos. One, I have stability to be in the narrow. And all three, entropy, Lempel-Ziv, and Lyapunov, they can feel it. And then, because again, I was trying to target these to undergraduate students, I said, all right, guys, let's do this. Let's use Markov partition, right? Let's use Markov transition matrices to understand what's going on. So for example, If I turn around this right wing and then switch to the left, and if I have probability of switching to the left and probability of staying on the right wing is roughly 0.5, 0.5, which means, hey, I'm tossing a coin, right? I can't make it more chaotic than that. If my coin is biased, right, I do know like 2/3 of the time I'm going to switch between the wings, right? I know what's going to happen, right? I can make a better prediction. And of course, you can get a periodic orbit that has a Markov partition 1/2, 1/2. But then, because again, if it's stable periodic orbit, it's got to be Lyapunov stable, of course, right? If it's Lyapunov stable, it means it's a normally hyperbolic, which means it exists. Its stability window is some kind of interval. And as you can see in this area, I'm using Markov partition to tell that, oh, that's stability window. So basically, you can use that approach to detect stability windows too. I mean, it has drawbacks, but also it has certain pros. Okay, and this is the original Lorentz model, and these are the T-points in the Lorentz model, right? Let me just say a few words about this. So basically, the meaning of this T-point would be the following. Okay, let me go back to the previous slide. Sorry for the switching back and forth. And okay, so T-point means that you have unstable separatrix of the saddle, okay, and then you release it, and it goes around, and then it hits the saddle focus, either on the right or on the left. So this is called heteroclinic connection, one-way connection. But the unstable manifold of the saddle focus is two-dimensional, and so is the two-dimensional unstable manifold of the saddle, which means in 3D they intersect transversely, which means this heteroclinic connection is okay, is of codimension 1 because of two trajectories, one-dimensional should merge in a 3D. So this corresponds to the T-point. And the theory is the following. If I've got that, if I perturb a little bit, okay, then I follow the spiral away from the saddle focus. And then by little perturbations, it means that I can follow this path and I'm going to come back to the saddle focus again, which means it's a Shelnikov saddle focus, right? In general, it means that you have infinitely many small horseshoes nearby, but there is a little drawback of having a Shelnikov saddle focus in 3D, and namely, it causes what's called heteroclinic tangencies that result in a saddle node bifurcations, and then you have a periodic orbit. They can be narrow and long, but still they exist, right? That's why 3D systems with Shelnikov saddle focus, they're not really truly chaotic attractors, right? Because of the presence of the stable periodic orbits. And that basically means that as soon as you have saddle focus heteroclinics here, that's why you have the stability windows. And this is another part of the story. This kind of bifurcation is called inclination flip of dimension 2. I just skip it, right? I mean, what time is it? I have 7 minutes to complete this. Okay, so what I said about saddle focus is true for the Rössler model. As you can see, this projection, it doesn't have any window in the middle, which means trajectories come close by the saddle focus, which means these are homoclinic bifurcation nearby. And what you see here, this is the sweep done by Krishna using what's called long-term symbolic sequences. Again, you run it, the solutions for a while, then truncate and look at the end. And then you have to say, okay, my sequence after that, is it periodic? If it's periodic, that means I'm sitting in a stability window, this one, or that one. Some people call it shrimp, okay? Or you're in a region of chaos. And the truth is that these shrimps, the stability window in system with saddle focus, they're everywhere. They're scaled down, they're small, but they're everywhere. So you never know a priori whether you're going to end up on a chaotic attractor, or if you change slightly your system, whether you're going to end up on the periodic orbit, okay? And so maybe I'm going to skip this part. That's this theory that I mentioned to you earlier. I should have shown this picture before. This is saddle focus, okay? That's how 2D map looks like. And this is 1D map. And what I meant is that if you change the parameter, then this critical point, if I lower it a little bit, is going to create a saddle node, and therefore you're going to get a stable fixed point on the right, which means these are the cause of those stability windows in parameter space. Okay, and in the same way, you can introduce symbolic dynamics for the system with saddle focus. Let me give you an example. This is called a primary saddle focus. So the loop, you go and come back. And then in this case, you see you slightly miss it, right? And you're still above the stable manifold. And then you go on a second round and then on the second round, you can land your plane on the ground, right? Which means it's a double loop or secondary loop, and we can introduce symbolic representation for it. We call this 1-1. Okay, and then this is triple loop, 1-1-1. Okay, and when you miss the primary loop and you go underneath, then you come back to the saddle focus. Okay, we introduce this as a 1-0. And you got the point, right? This case is going to be 1-1-0, so which means you travel twice above the saddle focus and then go underneath. And that's how one-dimensional maps looks like. So, and you don't have to use this for symmetric system. For symmetric system, it's easier because you don't have to worry about solutions running to infinity, but you can always use, for example, one-way sequences, right? So, but this is a symmetric system. It has the mirror symmetry. It's a three-dimensional system, right? And then we want to find out, okay, everybody knows that if you have a primary saddle focus heteroclinics, you have secondary, right? They all fill in densely in a Banach space, in parameter space, right? And how they look like. And this basically shows you how they embedded in a parameter space, not for this particular choice of the model of the system, but it's true for almost every system with shielding of saddle focus. They all look like U-shaped curve, okay? And then there are similar U-shaped curve corresponding to the same symbolic representation, but for the smaller pharmaclinic orbits. And that's how you can use long-term binary sequence to detect stability windows. So if you use short-term sequences, you want to disclose the fine organization structure of homoclinic heteroclinic bifurcations in a system under consideration. If you use long-term, it's going to give you basically the answer where you have stability windows and when you have really chaos in the system. Okay, and then I go back to Krishna and just a few slides. So it's another example that was always on my mind. I knew this example from early 90s. It's known fact that Lorentz attractors were observed in nonlinear optics, and this is one particular system. Okay, these are equations, right? But you can see it looks like Lorentz attracted this, and this is due to again Krishna. You use the same symbolic representation. Okay, that's how you introduce the color map. And if the sequence is, this value of the power series is close to 0.4, you're going to get this 0.5. And as you can see, you have this spiral structure. But the question is like, where do they come from? And the answer is that all these structures come from this little point over here, which is called codimension to homoclinic bifurcation orbit flip, when your orientation of the stable manifold changes, or it's called strongly stable manifold changes from a cylinder to a Möbius band. I'm not going into details here, but again, I know the theory at this point, and that was my PhD back then, and in the similar things. But again, there is no way back in the early 90s I could have created something like that, because again, it's so expensive to do that. And then we talked to the guys who developed a piece of software known as MatCont. And Hill, who's a friend of ours, right? He's a professor in Holland, and he's one of the creators of MatCont, designed specifically to trace down homoclinic bifurcations. He used Krishna sweep to reconstruct these lines one by one. But keep in mind, he designed that code, or he co-designed, which means he's an expert, plus he's Dutch, which means he's very patient and very skilled, because there is no way I can do this, right? And it's not worth it, right? And then, because clearly you can see that something is going on, right? And I know theory at this point, I know theory at this point, I know theory at this point, I know theory at other points, but how to put it together, right? It's a big interesting question, right? But at this point, I don't want to go into fine organization of this homoclinic bifurcation. Just tell you that if I have your interest, we can talk about this later. And how to say that, GPUs let you do even more. Okay, so they can let you create what's called three-dimensional bifurcation diagram. We used to be in a plane, But if you remember here, right, these are, okay, I don't know. So between 2 points, these always a saddle. Let me just see, yeah. I saw it. You see that saddle over here? Okay. And then you can ask me why, for example, this structure looks like a spiral, why this looks like concentric circles. And the answer is that straightforward, right? You need to go to Whole Foods and buy veggie, cabbage, okay? And if you cut it through the middle, guess what you see? You're gonna see the spirals, right? Embedded spirals, right? That means this curve I'm embedded compactly in a plane, right? In a compact subspace. And if you cut it not through the middle, right, but kind of in parallel, you will get concentric circles. And that basically, I mean, I know it's kind of funny answer, but that's how it works. And in an old paper published in 1992, I sketched some kind of what the role of the saddles, right? And the saddles basically redirect this bifurcation diagram in three-dimensional space. And Krishna numerically reconstructed my hand drawings. And as you can see, it's just it was my hand drawings. I'd taken out of how I envisioned that. And he created this saddle in a three-dimensional parameter space of that nonlinear optics models, which means the GPU simulations are so fast, right? If you're skilled enough, right? And Krishna definitely is super guru in this case, right? You can create bifurcation diagrams. You can figure out what the saddle means. It's just a hyperbolic paraboloid, right? And things like that. It's fun, okay? And also you can even see. Let me see. Can I run this? It's supposed to be a movie showing how the bifurcation diagram changes as you change the parameters, right? The third parameter in the system. And that's your primary T point. And you can see how the amplitude of these wiggles going to increase, and then they're going to merge to form spirals, right? And again, the GPU speed and GPU acceleration let you play with such models, right? And okay, this is supposed to create a movie that is the sound, but again, that's enough. All right. So in case if you had questions about homoclinic bifurcations, I preserved this slide, but I rather stop here. It's already 5 afternoon, and that should be enough for.
Thank you very much. Let's thank the speaker, everyone.
You have chats.
We have not a lot of time, but maybe there's time for at least one question. If you have a question, please let us know in the chat or any of these type of questions. So let me stop the recording just in case.
Okay.
There's people.